Good evening. I'm Dr. Andrew Finstuen, Director of the Honors College here at Boise State University, and welcome to the Distinguished Lecture Series. Before I introduce tonight's speaker, I want to mention a couple little logistical things. First off, please silence your cell phones. Secondly, following Dr. Solomon's remarks, there are microphones at either side of the video table here, and she will take questions at the end of her remarks. And we'd like, if there are students, we'd like to reserve the first two questions for students, and then thereafter we'll just alternate the microphones as far as Dr. Solomon's moderating of the Q&A session. And finally, there are some little surveys on your seats, some information we'd like to gather just in terms of how you heard about the Distinguished Lecture Series or this particular lecture in particular. And then also, if you'd like to join an emailing list, that's fine, and we only use it for these purposes. But we'd like the feedback, and we'll just collect them in the tables if you can just drop them off as you leave after tonight's lecture. Thank you. The Honors College is proud to produce this lecture as another form of its service to both the university at large and the wider Boise community. The Distinguished Lecture Series, as many of you know, consists of an annual fall and spring lecture, which brings eminent scholars, world leaders, and activists to Boise State and to the community. The series has featured Nobel laureates, former heads of state, and other renowned academic and civic leaders. We are pleased tonight and privileged to welcome you all to A Tale for Our Times, Something for Everyone About Climate Change and the Reasons for Climate Gridlock, featuring Dr. Susan Solomon. If anyone is qualified to address the issue of climate change for us tonight, it is Susan Solomon. She is widely recognized as one of the leaders in the field of atmospheric science. And let me give you just a brief outline of her credentials and accomplishments in this field. Until this last year, Dr. Solomon was a scientist at the National Oceanic and Atmospheric Administration in Boulder, Colorado, and an adjunct professor at the University of Colorado. She now joins the faculty of the Massachusetts Institute of Technology as the Ellen Swallow Richards Professor of Atmospheric Chemistry and Climate Science. She is well known for having pioneered the theory explaining why the ozone hole occurs in Antarctica and obtaining some of the first chemical measurements that helped to establish the chlorofluorocarbons as its cause. Solomon's research has helped institute a global ban on chemicals that destroy atmospheric ozone and threaten human health. She is the author of several influential scientific papers in climate science, including one on the irreversibilities of the climate change problem, as well as a popular book on Antarctic history entitled The Coldest March. And I think we're pretty confident in this next piece, she is probably the only speaker we have had for whom a glacier in Antarctica has been named. She is a member of the National Academy of Sciences, the French Academy of Sciences, the Royal Society, and the European Academy. She has received the National Medal of Science, the highest scientific distinction and honor in the United States, as well as the Grand Medal, highest award of the French Academy of Sciences, the prestigious Blue Planet Prize in Japan, as well as the Volvo Environment Prize. She served as the co-chair of the Climate Science Group of the Intergovernmental Panel on Climate Change, IPCC, from 2002 to 2007. And as part of her work with that committee, she and the other committee members won the Nobel Peace Prize along with Al Gore for their work in raising awareness of the risks of climate change. In 2008, Time magazine named her one of the 100 most influential people in the world. And with all of this in mind, I can add that Dr. Solomon's interactions with myself, with students on this campus, with faculty on this campus, has proven her to be an attentive listener, a careful and curious observer. As we've walked around campus, she has pointed out multiple natural and structural elements of the campus that I hadn't noticed. And most importantly, a gracious scholar. Please join me in welcoming Dr. Susan Solomon to the podium.
Well, thank you so much for that very, very warm and wonderful introduction, and thanks to everyone for the several fantastic times that I've had here on the Boise State campus. I've been so impressed with the students. It's really a very enthusiastic and special group of young people that you have here, and an equally enthusiastic and remarkable group of faculty. So it's really been a tremendous honor. What I want to do tonight is to talk to you about climate change. I'm going to talk to you about the science of climate change. I'm also going to talk to you a little bit about some of the human aspects of climate change and climate policy. And in starting that, one of the first things I want to do is to just show you how extensive the warming of our planet really is. This is just a graph of how the planet has warmed over the 20th century. And you can see that almost every place on the planet has gotten warmer. We have a remarkable suite of measurements. I'm really always so inspired whenever I show a graph like this to think about the fact that there's so much data covering such a large fraction of the planet. And I'm going to talk a little bit about where that data comes from in just a moment. But what you can certainly see when you look at this is that the red is covering just about everywhere. Not totally everywhere. There are places like this area just south of Greenland where we think that the ocean has changed a little bit, and actually a very interesting area in the southeastern US where, interestingly enough, it hasn't warmed like much of the rest of the world, probably in part because of changes in land use there, because of the way that we cut down all the forests in the southeast, but they're actually now growing back, and that's actually cooled the southeast a little bit. But just about every place else, what we find is a tremendously extensive warming. It extends out over the oceans. When you look in places like down here in the Atlantic, you know, it's very clear that it's not confined to urban areas. I'm going to talk a little bit more about that in just a minute. If you go ahead and globally average those numbers, this is what the temperature record looks like, computed by several groups. So it's showing you the change or the difference relative to the average over the whole time. And so you can see the warming that's happened. It's about 3/4 of a degree Celsius, or about 1.3 degrees Fahrenheit, warmer on average across the globe than it was, say, in the late 1800s. There's a period of rapid warming in the early part of the 20th century, then this period of relative flattening. That period's really interesting, actually. What probably happened then is that there was a lot more particulate matter, a lot more haze in the atmosphere, because we had really bad pollution problems back then, 60s and 70s. I can remember when I was a kid how polluted things were. In Los Angeles, people talked about not even being able to see across the valley because there was so much pollution. There was literally a haze of pollution over the whole northern hemisphere. It was reflecting sunlight back out to space and cooling the planet a little bit. And so that actually offset the warming for a while. But then we cleaned up our act because we got concerned about pollution and what role it might be playing in terms of human health, especially the particulate stuff gets in your lungs and it's very bad for you. So the Clean Air Acts in the United States and pollution measures in Europe all kicked in, and you can see the very strong warming that has happened in the subsequent few decades. I'm not saying that there isn't some component of natural variability in this, but I think, as I'll show you later, there's strong evidence that most of that warming is due to human activities. If you have a look at the sequence of warm years, and I apologize for not having the last two of them up here on this list, they are both in the top 15. What you can see, though, is that you have to go a long way down this list to find a year in the top 25 when most of us weren't alive. And if you're a student here, you probably can't find a year when you were alive that isn't actually in, say, the top 20 if you're 20 years old. So it's really quite remarkable how we are currently living in the warmest period in the instrumental record. One of the issues that's been questioned is whether these data might be wrong due to urban changes. So the fact that there's been urbanization, and we all know about urban heat islands in cities. Cities do get warmer than the surrounding countryside, but that's not where these data are coming from. We're very careful in which data sets we use and how influenced by local urbanization they actually are. And in fact, you can go one step further. You can actually find stations where there is no urbanization at all. The beauty of that is that we have the wonderful night lights of the world records now from satellites. So we can actually look down on the Earth from space, and we can see exactly where all the lights are. That's where the people are living. That's where the urbanization is happening. And we can pick out what I'm going to call the pitch black stations. So from those of you that are into modern culture, we're going to call these the Vin Diesel stations. It's a great movie. I really loved it. But even in the United States, we can find quite a few of those pitch black stations, and we can have a look at just those versus what we get if we use all the stations that have been corrected for urban influences. What you see is that with the night light adjustments, those are over here on the left, no adjustment over here on the right, they're virtually the same. We could also choose to adjust by population, just pick out the stations where the population is less than, say, 20,000 people, and that's what's in the middle. You can see with your eye that these are very, very similar. If we go ahead and globally average those, once again, those are all three of those data sets, whether it's the pitch black stations, the population adjusted, or the unadjusted data sets, they all show very much the same levels of warming. And we don't have to just rely on the thermometers. We also have these wonderful records of what has happened to glaciers. And I know that here in Idaho, you're beginning to become concerned about the retreat of snowpack in your mountains. The same thing, of course, is happening to glaciers and mountains worldwide. What's great about glaciers is there's a lot of them. They're on just about every continent in the world. And there was a recent study of the retreat of 169 of them. And by and large, they showed warming consistent with the thermometers. I'm not saying you could make that case with a single glacier. There are exceptions. Glaciers in Norway, for example, have actually advanced, and the reason for that is that there's been an increase in snowfall in Norway, which is unusual. Most places have the snowfall change, if there is one, has not been enough to outpace the melting. But Norway is one of those exceptions that proves the rule in a sense. This one that I'm showing here is a glacier in the Cascades, and you can see how the glacier came down all the way to the valley in 1912, and it now barely is getting out of the upper part of this particular region. I believe it's in the Cascades, actually. And if we have a look at what's happened to glaciers, what's nice about that is that in some places we have observations of the extent of glaciers that goes back 500 years. So, we can go way back in time to see what's happened over the centuries. And this is what that's showing you. For the first 400 years or so, not very much was happening. On the Alps, in the Andes, in North America, that's what the different colors are. But then in the 20th century, they all began to retreat. And the amount of warming that corresponds to is shown here. It's very similar to what the thermometers are showing, which is the solid heavy black line. So glaciers are a great way to use the natural world to see what's going on. Well, here again is that record of temperature change. And now what I'm going to do is just pick out the last 10 years, which is what some people have done in articles on the internet, and they've said, gee, it doesn't look like it's warming in the last 10 years or so, so maybe this global warming stuff, maybe that's just not true. That's not really the right way to look at it, and let me show you why. We could pick out another set of 10 years, and you'd see ups and downs in that one too. Or we could pick out another set of 10 years back here, and we'd see ups and downs in that as well. So, if you took any one of those 10 years in isolation, you might say the world isn't warming. But it's very clear when you look at the 30 years taken together that the world's very definitely warming. And so that's really beginning to point you towards the difference between weather and climate. Weather can cause variations from one year to another. You can indeed have hot years, cold years. But climate is what's causing changes over multiple decades. And so are there ups and downs from year to year? Yes, that's absolutely true. Is it relevant to the global warming problem? No, it isn't. And honestly, when I look at some of the things that are out there on the internet that are confusing, I often find that it's this kind of problem. People are talking about things that are strictly speaking true, but which are actually not relevant for climate change. And I'll show you another example of that in a couple of minutes. So where do these data come from? It's just amazing how many records we actually have. And I find it really quite inspiring to me as a scientist when I look at a map of the world like this. Those little dots, those are all places where records have been kept for at least several decades, and in most cases more than a century. So it's pretty amazing how much data there actually is. There's also ship data, but these are all the land stations. They're just about everywhere. In the United States, you can see how extensive our coverage is. I mean, you can barely actually see the states because there's so many dots in the US. Well, who do they come from? It's actually not from mad scientists who are cooking this stuff up in the lab. This is an example. This is a lady, Mary Jo, and her husband Jim, and they live in Alaska, and they operate a seaplane. So they live in a very remote part of Alaska, and they take measurements in the little cove where they land their seaplane, and they've been doing that for some 25 to 30 years. This gentleman is one of my favorites. He's actually accepting an award here from the National Weather Service for 100 years of service. Of course, he isn't 100 years old, but what has happened is that on the family farm, which is in a place called Philo, Ohio, he has been taking measurements, as did his father, as did his grandfather, and the family has, on this farm where nothing has changed in a long time, I bet, has been taking measurements. And just looking at Mr. Burkholder, I must say that I would not mess with his temperature record. I don't know about you, but so if you have a look at his measurements, you can see that there is indeed, it looks like a little bit of warming that's happened in that particular spot. I wouldn't make too much of that, and I'm going to come back to it. Here's another one of my favorite weather observers. He's actually a gentleman in Georgia whose house caught fire. And as he was racing out of his house, I sure hope he got his family photos and his cat. But what he also did get was his weather records. And that really tells you something about how these people feel about the work that they're doing for you so that we have climate records. Okay, what about our own backyards? This is the question that we all want to know. What's happening to climate where we live? And how do we understand this difference between, weather and climate? Doesn't the temperature always change? Sure it does. We see on the TV weather fronts pushing down over, say, Idaho. It can get very cold in Idaho. Typically that's when cold air comes out of the north to the south, out of Canada to us. But all that's doing is pushing air around. It's making it colder than it would normally be in Idaho. It's typically making it warmer than it would normally be, say, to the east over, say, New York City, because it's just pushing air from one latitude to another. It's not a net change in energy. So it's tremendously variable because of that in space and even in time. And so we have to average over space and time to find out what's going on to the climate. The fact that we have local variability shouldn't confuse us between weather and climate. So here again is the warming. This is all the Januaries in all of those data points. And you can see the red ones are all where it's gotten pretty hot, at least by something like a degree typically. But if I drill down into a point, say in Canada, I'm going to see a lot of variability in the Januaries. It looks like there's maybe a trend, but there's hot Januaries and cold Januaries. So it's superimposed on a tremendous amount of up and down. And what that means is that we shouldn't overreact to the fact that, hey, we've had a warm winter. That doesn't mean that we're seeing necessarily the effect of climate change, but neither does a cold winter, because it's happening against a backdrop locally of a lot of variability. Same thing is true, say, in Australia. Same kind of thing would be true in, say, an area near Paris. Same kind of thing near Denver, not too far away from here. Notice, though, that in Denver, you may be able to notice that actually the coldest Januaries aren't quite as cold as they used to be. I'm going to come back to that in a couple of minutes. But the key thing is really shown here. When we go ahead and average over the whole planet, look how the variability goes down, because now we've averaged over the way those weather systems, those fronts, move air around. And you can see very clearly that the globe has gotten warmer on average. Each of these places, on average, has gotten warmer too, but not you can't judge it by an individual hot or cold month. Well, what about extreme hot summers? To what extent can that be attributed to what we're doing? This is a picture that was taken, I think, in New York City. During heat waves, they used to actually truck in ice, and everybody would kind of gather around the ice to cool off. So indeed, hot summers have been going around for a long time. We can't take a single hot summer as an indication of anything really odd. But if we pick out a point near Paris and look at all the summers, notice how incredibly hot 2003 was. That was the record hot year that actually killed about 10,000 people in Europe, mostly elderly people who, frankly, were not drinking enough. Nowadays, because this has happened, people are much more aware. They're taking much more careful steps to hydrate themselves. But at that time, I think the awareness level, people just thought, hey, this is Europe. It doesn't get that hot here. But you can see that 2003 was very, very warm, very unusual, and it was superimposed against this backdrop of warming. So indeed, much of the influence was just the variability from one summer to another, but it was a little bit warmer because of global warming by about a degree or so. And that very hot summer that killed all those people was actually only about 3 degrees warmer than an average summer in Europe. So on average, it's not that big a difference, but it makes all the difference because, for example, it affects things like whether or not you have the opportunity to cool off in the evening. Those hot summers, just, even though the average number is not that much greater, it's enough to make a big difference in the comfort zone. Well, one of the things we can do, and let me just back up 1 second here, is take all of those summers and lay them out and figure out what the distribution looks like. So if you remember being graded on the bell curve when you were in school, the average was a C, and some kids got A's and some kids got F's. So here's the bell curve of summers in Europe. And so the average is right here in the middle, and the cold years are over there to the left, shown as blue, and the hot years are over to the right, shown in red. And what you can see is that Europe has had an awful lot of hot summers recently. Almost all those hot years are recent years. 2003, the one that I mentioned. 2010 was another very hot summer in Europe. But also 2002 is there, 2006 there. So, there is a shift in that distribution that's happening. And most of the cold years are years that happened a long time ago. Why is this happening? Well, this is actually really interesting. If you think about that bell curve business again, the class being graded on the bell curve, if we shift the bell curve over, it doesn't make that much difference to the average, just shifts it over a little bit, but it makes a huge difference in the tails because things that only happened infrequently now are happening much more frequently. So, for example, a shift of 1 standard deviation will make a 1 in 40 year event into a 1 in 6 year event in this example. And that's what's happening to European summers. Those hot summers are happening just a lot more often. If we look to the future in Europe, by the time we get out to, say, 2050, almost every summer is going to be as hot as the hottest ones are now. And the hottest ones will be even hotter. So it's going to get very, very hot in Europe. What about the United States? Well, I'm going to briefly take you on a little trip through a fascination of mine, which is meteorological history. It's also a lot of fun. Interest in climate science has a tremendously rich American history. You might recognize these gentlemen. They're the guys the committee that wrote the Declaration of Independence. Mr. Jefferson is seated. You can see Mr. Franklin. You can see Mr. Adams. I used to know the names of the other 2 guys, but I forgot them. They actually were great guys, too. But this is an image of one of the drafts of the Declaration, and it's in Mr. Jefferson's handwriting. What's really interesting about it, because it is a draft, is you can go back and look at the things that he changed. So what was the original language and what decisions did they make about the final language? This is available online at the Library of Congress website, and I really recommend it. What you can also get online is this, which is a page out of Jefferson's weather book. Mr. Jefferson started taking measurements of the weather every morning and every evening when he was a young student at what later became, I believe, William and Mary University College. And he did it basically his entire life until he died. So every day he would record the morning temperature, the afternoon temperature. He would write things down like what kind of flowers were in bloom, what kind of birds he saw. He also wrote frequently to men of science all around the world. I'm sorry to say there weren't any women in science that he wrote to back then, but I'm sure he would have written to them if they were around. And things in those letters are beautiful to read too. It's relevant to this issue of European summers and why they're having hot summers, and we're so far not experiencing quite the same thing. And back then, in 1805, Jefferson himself had noticed that the changes between heat and cold in America are greater and more frequent, and the extremes span a greater scale on the thermometer in America than in Europe. So what he's saying is our climate here in America is more variable than in Europe. And of course, that's because we have a highly continental climate. We're heavily influenced by the big land mass of North America. Europe is much more influenced by the surrounding ocean. It's smaller, it's close to the water, it's influenced by the Gulf Stream. All those things lead to a more moderated climate. And then he went on to say that habit prevents those hots and colds from affecting us as much as the smaller changes in Europe affect them. So he was actually beginning to understand something that today we would call climate change adaptation, that when you have a very warm summer, you do begin to adapt. So the effects of climate change are going to be moderated in places with a lot of variability, probably. I wrote a little paper about this in American Scientist that you can have a look at if you're interested. But another thing I want to tell you about is the fact that in Virginia, not only did Mr. Jefferson do great things, but of course he had a good friend, James Madison, who later also became president, and they jointly wrote the Bill of Rights together. But the other thing that they did jointly was to measure temperature, because Jefferson asked Madison to please get a thermometer and to make measurements on his plantation, which was in Montpelier, very close to Monticello. That's a little map of Virginia. You can see I've marked Monticello and Montpelier on there. And those little A, B, C, and D are some of those modern weather stations. People like Mr. Burkholder in Ohio, there are weather stations located quite close to where Jefferson and Madison lived, where people are today taking measurements. And there is a page out of Mr. Madison's weather record. Typically what those weather stations look like, it's not a very complicated instrument. It's just a box with painted white so it doesn't absorb sunlight, with little louvers on the side so air can pass through, and the thermometer sits inside. And this is just an amazing thing to me. So here are the monthly averages of the measurements by Jefferson and by Madison. Whoa. Oh, please. No, I don't want to register right now, thank you. Okay. By Jefferson and by Madison, and you can see the relatively cold Virginia winters and the much warmer Virginia summers. And you can't really tell the difference, probably from where you're seated, between Jefferson and Madison's measurements and the averages of the data from Charlottesville and Monticello and Piedmont Research Station, which are those stations very close to where they were located. So it's really quite amazing to me that they could make measurements that good 200 years ago. Isn't that something? By the way, it is actually a little bit warmer based on this record now than it was then. I wouldn't make too much of that. There's only about 12 years of Jefferson's data, and I think about 20 years of Madison's data. We've actually lost some of Jefferson's data. It's not, there's about 15 years that are just missing in the archives. It's very sad. I hope somebody finds it someday. But anyway, the key point to me is just for those people who question, can you actually make these measurements? Can you make them that accurately? Of course you can. The founding fathers made them 200 years ago, and they agree quite well with what we do today. So of course we can look for trends in good temperature measurements. And if they were interested in climate, I would argue we should be as well. Don't tell me this thing. Okay. Not just Europe. Europe is not the only place that is going to experience warmer summers. If we were to have a planet that would be, say, 2 degrees Celsius warmer than what we experienced before human activity really began to influence our climate. Essentially, the whole planet would be in a situation where 90% of the summers would be warmer than the hottest summer is now. So think of that, where 9 out of 10 summers was as warm or warmer than the hottest summer that you remember, and that's the situation that we'll get ourselves into. So this has attracted the attention of many different governments for obvious reasons. Very, very interesting and important political issue. And it gets to be more political when you think about the reasons for the changes, and even more political when you think about what you might want to do about it. I'd like to keep the politics of what to do about it, what it's going to cost, and indeed whether to do anything at all, separate from the science of, what is actually happening. What do we know about how it's warmed, and what do we know about why? I'll talk more about that as we move along. So what could be changing the temperature on our planet? Let's just talk about the atmosphere a little bit. And in order to do that, we should look at the composition, at what chemicals have been in our atmosphere. And a great place to do that is the polar regions. You probably know that Antarctica is a massive ice cap. When I've been to Antarctica to study the ozone hole, I like to tell people I can join the South Pole Ski Club, where I can ski on 3 kilometers of base and 3 centimeters of powder. It's really great. And you can dig a core, you can dig up an ice core and look at the bubbles in that ice core and measure the chemicals in those bubbles. The main one that we're interested in here is carbon dioxide. Carbon dioxide is a greenhouse gas. It absorbs infrared light that would otherwise cool the planet by escaping to space. There are some wavelengths of infrared light that the carbon dioxide absorbs that nothing else absorbs, and therefore it warms the planet quite a bit. So the planet has a temperature just like you and I have a temperature. If I had infrared glasses on right now and this room was pitch black, I could see all of you and as infrared objects. Our planet, same thing. Its temperature is radiating out to space, and carbon dioxide keeps some of that energy in. The amount of carbon dioxide back when 10,000 years ago, excuse me. This slide is showing you the carbon dioxide for the last 10,000 years. And for about 9,900 of those years, the carbon dioxide's about the same. It's about 270 parts per million. So in every million air molecules, you would find 270 carbon dioxide molecules. And then it goes shooting up. So when mastodons were on the planet, it was about 270. And when the Egyptians built the pyramids, it was still about 270. And when the Romans built the Colosseum, you get the idea. And then the Industrial Revolution happened, and the carbon dioxide went shooting up. So we have a higher concentration today than we've had on the planet in more than 10,000 years. I'm going to show you in just a minute, it's actually higher than we've had in 800,000 years. So a very, very long time indeed. That increase in carbon dioxide is a forcing of our planet's climate. It's changing the energy budget by keeping that energy in. So we like to speak of it as a forcing agent. It also acidifies the ocean because carbon dioxide is slightly soluble in water, and when it goes into the water, it acidifies the water. Oh, and I meant to mention, if you just want to get an image of how much warming the changes in carbon dioxide represent, think about a conventional Christmas tree light, not the new LED high energy efficiency lights, but the old style conventional Christmas tree lights. They were warm to the touch, and they generate about a watt of energy. The carbon dioxide increase that we've done on our planet is actually generating about 1.5 watts of extra energy on every square meter of the planet. So think of the whole planet being just completely draped, every square meter, in Christmas tree lights, and that's the extra energy. It kind of seems pretty, doesn't it? But maybe it's not so pretty, as we're about to talk some more about. So that's the record over 600,000 years. You can see ups and downs associated with the ice ages, and I'm going to mention some more about that in just a minute. That's what's happened in the last 150 years. It's just gone completely off the charts from any CO2 levels that we had in 800,000 years. And you can see in that picture the little bubbles that exist in the ice core that allow us to make these kind of measurements. Well, one of the things that people say is, gee, well, there's been ice ages before, so climate's changed before. Why should we worry about climate changing now? Is it true that climate has changed before? Absolutely yes. Is it relevant to what's happening now? I think you should be the judge of that, and I'll tell you a little bit about it and let you judge it. So if we have a look at what's happened to those past ice ages and warm periods, and that's what I'm showing you here, they're very regular. They're not like mood swings. It almost looks like a clock. We had an ice age 20,000 years ago. We had another one 100,000 years before that, roughly, another one 100,000 years before that. They happen roughly every 100, 110,000 years. And what that's caused by is actually the Earth's orbital clock. It looks like a clock because it is a clock. And the way it works is that the parameters of our orbit change very, very slowly under timescales of literally tens of thousands of years. And there's an example, an exaggerated example of what happens. The distance between the sun and the Earth actually changes. This is a very exaggerated cartoon, but at least it'll give you an idea. And just want to play it for you. I guess maybe I can't play it for you again. Sorry about that. Oh, maybe I can. There we go. So the distance between the sun and Earth changes on a time scale of tens of thousands of years, actually about 40,000 years. The other thing that happens is the angle between the sun and the Earth also changes. Both of those factors combine to produce the ice ages. So what's happening is very slow changes in the Earth's orbit are changing the energy driving the climate system. And the fact that those changes actually lead to ice ages, to my mind, confirms that changes in the energy budget will force the climate to change. So it's not a mood swing, it's something happening in response to a change in the energy budget. And what that means is it's all the more reason to ask what our changes to the energy budget, our man-made carbon dioxide that we're adding to the system, is doing to our planet right now, because the orbit isn't changing now. That's not what's happening on these fast timescales of decades or half a century. The next ice age is not going to start for many thousands of years. It's not the orbit that's changed since 1900, it's our carbon dioxide that's changed. Well, what about the sun? Is it possible that maybe the sun has gotten brighter? The bottom line to that is shown in the bottom panel here. The sun does have an 11-year cycle of ups and downs. That's related to magnetic activity in the sun. So it's a little brighter, and then 5 years later it's cooler, and then 5 years after that it gets brighter again. So there's an 11-year cycle in it, 5 or 6, I should say, in those differences. But what you can see is that the brightness of the sun hasn't changed since the late 1970s when we began these very good quality satellite measurements. So it's not changes in brightness that's causing the warming that we now have. There is also no observed change in cosmic ray fluxes, which is also related to solar activity and is another thing people bring up. Okay, well, let's just talk about how well we can model this. There again is that temperature record globally averaged for the last 100 years or so. That's what would have happened with only natural processes at work. The sun actually stayed about constant, but we did have several very strong volcanoes. And what's cool about those is that they reflect energy back out to space, just like that haze that I was talking about that we put there in the 60s and 70s. And so what they did, those very energetic major volcanoes, was to cool the planet a little bit for a little while. That's the only natural forcing that you really see doing very much there. So that when we add up the natural forcings and the man-made forcings, we get a plot that looks like that. And to me, the fact that those volcanoes come through is once again proof that if we change the energy budget, we will change the planet's climate. And the major factor, though, is not the volcanoes. They've only caused little transient coolings. It's actually the human activity, the increases in greenhouse gases. So what most scientists who study this problem, I think, would agree that most of the global warming of the last 50 years is very likely, something like 9 out of 10 odds, to be due to increases in anthropogenic greenhouse gases. Well, do greenhouse gases really warm the planet? Again, let's have you be the judge on this. One of the things I find really nifty about our solar system is that the surface temperature of Venus is actually hotter than the temperature of Mercury. Isn't that amazing? Even though Mercury is closer to the sun. The reason for that is that Venus has an atmosphere with a lot of carbon dioxide in it, also a lot of sulfuric acid, and it has an extremely strong greenhouse effect. It actually keeps Venus about 500 degrees Celsius warmer than it would be if it had no atmosphere, and that's why it's warmer than Mercury, even though it's farther from our sun. Our own Earth would be about 30 degrees cooler without our atmosphere's greenhouse effect, so having a greenhouse effect in that sense is good because otherwise we'd be frozen. But the extra greenhouse effect is the issue here. By putting more carbon dioxide in the planet, we have done something that has to warm the planet more. So how much more and what are the impacts? That's really what we should be talking about. So let me talk a little bit briefly about some of the impacts for you here in the West. In the Mountain West, I think one of our big issues is going to be fire. If we have a look at places in Canada where there is no forest management, so it's not an issue of forest management, there's been a marked increase, and that's what's shown in that little insert there. There's been a marked increase in wildfire in the last 50 years. The area burned has increased very much in concert with the way the area has warmed. If we look at the same thing in the U.S., what we find is that indeed in the U.S. too, it has, we've seen a big increase in the area burned. It's not more locally than the area burned was, say, in the 30s during the Dust Bowl when it was very hot in the U.S. But that was just a local U.S. issue. What's happening now is much broader than that, as I showed you. The warming is not just over North America, it's over the whole world. So if we were to warm another 1 degree, the map over there on the right shows you the type of change in wildfire that we would expect based on the past behavior. So it's basically determining what the climate sensitivity of wildfire area burned is to warming based on the ups and downs in the past record. And it fits very, very well. And what you find if you do that, some of these brown areas in Idaho are places where we, your high forests, we expect to see very large area burned increases, as much as a factor of 5 times more area burned if we warm another 1 degree. We've already warmed about 0.75 degrees Celsius. Another 1 degree Celsius would perhaps, would be expected based on our best understanding to give you a massive increase in wildfire area burned here. Would that be the end of the world? No. We'd have a different ecosystem. Idaho would be a different Idaho. It's not Armageddon, but it's a big change, and that's the way I like to describe it. You can see that many other regions are looking at 3 and 5 times more area burned. The places actually with relatively small increases in area burned are just simply places where there isn't that much vegetation. So it's already semi-desert, and you can't burn what's not there. The pine beetle is another issue for not so much yet here in Idaho, but very much in Colorado, where I've lived for a number of years. And in Colorado, we're seeing a massive die-off in our pine trees. There's a lot of reasons for that, but certainly the warm and dry winters that we've experienced, the reduced moisture has stressed the trees, especially the lodgepole pine, which is very sensitive. Big difference is the longer beetle breeding season, and I think this is beginning to be apparent everywhere, actually, that spring is coming earlier, fall is ending later, so the summer, the period of warm season is lasting longer. For the beetles, that makes the difference between breeding once in the summer and breeding twice. They can actually go around and do it again, which has caused a huge population explosion in the beetles. Also, there have been fewer extreme cold snaps to kill them in the dead of winter. When it gets below about -30, the little larvae that they leave in the trees actually dies. And we just very, very seldom have those kind of temperatures in Colorado now. We used to get them a lot. So different regions face different impacts. That's one of the reasons that this issue has been so stuck in gridlock. There's no one issue that you can say, this is the impact that clearly everyone should pay attention to. It's pine beetles in the Southwest, it's flooding in the East and Midwest of the U.S., it's losing your home because the sea ice has retreated and the sea has washed over you in places like Alaska, and water availability from reduced snowpack in places here like Idaho and also in California. So different impacts in every place. And are they the end of the world? No. Are they serious? That's a matter of ethics and judgment. I'll leave it to you. I will say this, that if you're a young person looking for an interesting career where you know that there's going to be lots of change and lots of dynamic things going on, climate change is a great thing to study. This is just showing you how the climate will be different on every continent by 2050. So the blue and the purple are the real changes and the natural range of the 20th century, and then the green and the yellow are what the 21st century would look like, the first half of it anyway, in a natural-only world versus the world that we're really going to have, which is the yellow. So we can expect the real world to become increasingly very much different from what it was in the past, and that's going to bring out all kinds of things. It's going to be a tremendously interesting world to explore scientifically. Let me talk a little bit about where those carbon dioxide emissions are coming from. The great bulk of the emission is from fossil fuel burning. Something like 15% is from the burning of forests, so clearing of forests in places like Indonesia and Brazil is significant, but 85% of the increase is from burning of fossil fuels, and we know that from isotope measurements. This is showing you the per capita emission. The good news is that we're not number one on this plot. We're actually, in this particular one, kind of, I guess the fourth one down from the top, at something like 20 tons of carbon per person per year in the United States. That's about double what it is in Europe. And you'll notice these countries down here, like Mali and Kenya and Cambodia, you can hardly even see them. They emit so little, but we're going to come back to them in just a few minutes. Why do we do it? Well, about a third of our use of fossil fuels is for the energy industry, about a third roughly is transportation, and about a third is everything else, and that includes industry and households and the service sector. So it's roughly a third, a third, a third. Now I want to go back and revisit those guys on the bottom, and I'm going to do that by turning this graph on its head. I'm showing you now the ratio of US per person emission to that of other countries. And it's a log scale here. I know that some people may not be familiar with log scales, but what this is telling you is when it's 10, it means that we emit 10 times more than that country. When it's 100, we emit 100 times more. When it's 1,000, we emit 1,000 times more per person than the average person does in Chad. It's about 500 times more than the average Cambodian. We emit about 200 times more than the average Ethiopian. We emit about 80 times more than the average Kenyan. So my flying here and flying back to where I live, I emitted about as much carbon in that one flight as the average Kenyan does in a year. And I do it a lot more than once a year, I have to say, with some chagrin. Places like India is about 20 times. We emit 20 times more than the average Indian. We emit about 4 times more than the average Chinese, as I'm going to show you in a minute. Integrated over the whole country, the Chinese emit a little more than we do, but they have 4 times more people than we do. So per person, we emit 4 times more than they do, et cetera. So basically what you can imagine is that people who live like that simply don't emit as much carbon as people who live like that or people who live like that. If we go ahead and average over the whole planet, the 6 billion people that are now in the developing world emit about 5 times less fossil carbon per person than the 1 billion in the developed world. So the question becomes, what about those people's future? I'm just going to quickly show you the total emissions, not per capita. That's us in the US, that's China, they've passed us, but not by much. That's Russia, that's India, that's Japan. So the reason for the big spurt in Chinese emission is not because they suddenly have a big spurt of population. Of course not. It's because they are now becoming much wealthier. They're doing a lot more business. They have much more industry. And one of the things that makes this issue so intimately tied to economics is that fundamentally it takes a dollar to make a dollar. You know, it takes money to make money, and it also takes energy. So what that means is that as China has become richer and their GDP has gone up, the carbon dioxide has increased along with it. So the question becomes, what's fair now? Should China pay more to develop by having to develop clean energy, which at the moment is more expensive? Should they pay more than we did to develop? Should Africa pay more than we did to develop? Should we come up with ways that we could all pay the same? How are we going to do that? How do we partition the past blame and the future blame? It's not an easy question. Let me tell you just one more thing about carbon, which is really interesting. If we have a look at how carbon dioxide has increased over the last 2,000 years, that's the plot at the left. I'm going to tell you now that a really useful way to think about carbon dioxide is it's like the water in a bathtub, and the amount that we're pouring in to that bathtub is the emission. The amount that the natural world can take away, taking it away to the oceans and taking it away, say, to make plants grow and stuff like that is another sink. So that'll be the drain. Those two things will be the drain. That's what the emissions have done. And if you ask the average MIT graduate student what we would have to do to the emissions to keep the concentration from continuing to increase, so to keep the water in the bathtub from continuing to go up, they would say we'd have to keep the emissions constant. So what that would mean is that we would have to stop cranking up the faucet so that there was more and more increase in emission every year. That's the wrong answer. The reason those MIT graduate students get it wrong is because the amount coming in through the faucet is about twice what the drain can take away. So even if we kept the amount coming in the same, the water in the bathtub would still go up, right? If we want the water in the bathtub not to go up, we have to not keep the emissions constant, but we actually have to decrease them by about a factor of 2. So the faucet, the stuff coming in from the faucet matches what's going out the drain. It actually gets a little worse than that. It's more like 80% than a factor of 2, but I'm going to leave it at that for now. Well, this means a massive change in our emissions if we want to avoid the world continuing to get hotter. What about geoengineering? Could we cool the planet by putting mirrors out in space or by putting a layer of aerosol particles in the stratosphere? People have talked about those kinds of solutions. I'm not saying that's impossible, but we do not have a workable solution in hand yet, so we'll have to decide what to do while we think about it. And another thing to think about is that 6/7 of the people on this planet are emitting about 5 times less than per person than the 1/7, which I already mentioned. So if they were to develop using conventional fossil fuel energy as we did, what's going to happen to the size of the water coming out of the faucet? It's going to be like that. It's going to be massively increased, and the planet is going to get very, very hot indeed. So I'm going to skip a couple things in the interest of time. I was going to talk a little bit about irreversibility of what's happening, but I'm going to skip that. So it's important to think about what's coming and how fast. You know, when you drive, it's really good to look in the rearview mirror because you need to know what's back there. I've talked about the bathtub problem. It's a very big problem. The emissions that we're producing today are much bigger than the removals. The faucet greatly exceeds the drain, and it's primed to get much worse because developed nations are emitting way more than developing nations, and it raises an enormous international issue because who's responsible for the past? Well, that would be us, the developed nations. Who's going to be responsible for most of the emission of the future? Well, that would be them, mainly the developing nations, but only because they want to live well as we do. They want to get out of that desperate poverty that they've been in for so many years. And right now, that's going to take energy, and that's going to take fossil fuels unless we decarbonize our energy supply, and I'll talk about that in just a minute. Commitments to infrastructure. We all have a lot of things we want to keep that emit a lot of carbon. You know, I'm not going to get rid of my car, probably not going to stop flying. I have a home that I heat, and that takes carbon. We have power plants that we're going to keep using, and they take fossil fuels. So can we fix it later? Yeah, but the climate change that we're producing now, I didn't really have time to talk about this in detail, but I'm just going to say that the warming that's already happened will last for more than 1,000 years, and that's because the oceans have absorbed so much heat, and they're going to keep giving it back to us. Well, I'm going to complicate the situation a little bit, but I also want to leave you with some hope. So I'm going to talk a little bit about a completely different problem, the ozone layer, which I've also had the honor to work on. It's a completely different story. We have a Montreal protocol to protect the ozone layer. An international agreement was signed in Montreal in 1987 to freeze and then to phase out chlorofluorocarbon emissions, which are what causes the ozone hole. I like to tell people that the only difference between the Montreal Protocol on the ozone layer and the Kyoto Protocol on the climate system is that the Montreal Protocol actually is working. What it has done has been to get to a point where today no nations are producing this stuff anymore, which is really amazing. You all probably remember those wonderful pictures of the ozone hole that came out in the mid-'80s, the records showing the ozone clearly dropping that various Antarctic research groups generated were really very impressive. You didn't have to be a statistician to be convinced of the ozone going away. That's me arriving in Antarctica. It was minus 40 degrees, and it was the most fantastic experience of my scientific life to do that work. So I'm going to now tell you a little bit about the politics of how we got to a Montreal Protocol that works. Maybe there's a lesson there for the Kyoto Protocol. And I'll do that by telling you about the negotiations. These are quotations from a book by actually the US ambassador who represented us in those discussions. And he wrote that skepticism about the theory, minimizing the possible harmful effects, that was the position of government X. And I'll tell you in just a minute who X, Y, and Z were. Government Y was similar. They had their positions coming mainly from the big companies and self-serving data, in his opinion. Government Z and their allies were the ones who came to every meeting and said, we must have a legally binding protocol, we must have timetables, we must phase out these molecules because they're hurting the environment. So which government was the skeptical one, X, and which government was Z, the one who was the environmentally minded one who actually led all the others to agree on a Montreal Protocol? Anybody want to guess? Okay, I hear some guesses out there. Here's the right answers. The most skeptical government was the UK, followed closely by the European Commission, mainly France and Germany. It was the United States government and its allies, which included Sweden, Norway, Canada, and Japan, who were the ones who led us to a legally binding international protocol to protect the ozone layer. So I think we should look back on that and ask ourselves, what does that tell us? Well, it tells us that this country provided some international leadership in the past on a very important problem. A lot of things led into that. I just want to tell you a little bit about what some of them were. What this is showing you are the sales of chlorofluorocarbons. The top solid line is the total over the whole world. The dash dotted is the rest of the world, and this is the United States. And so what you see is that basically it was only in the United States that the sales of these molecules started dropping in the mid-1970s. Why did that happen? Well, the Montreal Protocol was signed in 1987. Ozone hole was discovered in 85. It was in 1974 that the theory that said, hey, we might damage the ozone layer if we kept using chlorofluorocarbons was advanced by scientists. And people began to ask, well, really, what's that caused by? And the answer was, well, at that time, most of the use of chlorofluorocarbons was in spray cans. And it was mostly in your medicine cabinet. It was underarm deodorant and hairspray that was accounting for most of the US use. And there was a campaign, some of you, like me, maybe old enough to remember, get on the stick to save the ozone layer, right? So, we all got on the stick. And what ended up happening was that US emissions began dropping. That meant that what had been very good business for American companies became bad business, and any good company wants to get out of the business of bad business and into a different business. And the chemical companies in the US were nimble enough to say, yeah, we'll change. I don't believe the rumors that say that they had some sort of special intelligence and back pocket information and had a better substitute already in hand. I don't think that's true. I think we, the American consumer, put enough pressure on the American chemical companies that they decided that this wasn't worth hanging around for. And of course, they did make money off the substitutes. They're good businessmen. They figured out what to do instead, and I don't see anything wrong with that. So fundamentally, though, it was really us. It was really the American consumer that sparked the change that led to the Montreal Protocol. And it does show you the power that the consumer can have. But I want to hasten to say that in the problem of climate change, it's just not that simple. I recognize that very well. It's not as easy as giving up your, you don't even have to give up deodorant. You can just switch to the roll-on. I mean, how hard is that, in the case of climate change, it's really tough. My own footprint, I want to be honest with you, it's huge. I personally emitted something like 140 tons. I'm like a small African village all by myself. Last year, not because of my car, I have a Prius, but I fly an awful lot. I give talks like this an awful lot, and I hope they're useful. Well, what this is telling us too, I think, is that we've really got to get past all the forth and back of special social viewpoints and emotional reactions. It's kind of like an armed, village mob or something. There are people who use climate change as an excuse to argue for going back to a simpler lifestyle. Other people think that's a left-wing plot to control our lifestyles. Some people want to use climate change to alleviate world poverty. Other people think that's a third world raid on our money. People talk about the world flooding tomorrow. Other people think that there's a population bomb going on. All kinds of, you name it, people want to basically attach their issue to it. I think what we need in this discussion is what I would call some climate moderation. This is not an immediate catastrophe, but it is serious. It needs our attention, it needs our concern, and it needs our thinking about the ethics of the situation. It's not us who are going to suffer for this, it's future generations. It's not us here in North America where we're so nicely shielded from climate change because we have such a variable climate already and we're adapted to that. It's places where that isn't the case, and also places where they're simply too poor to have things like air conditioning, and in the case of places like Bangladesh versus Holland, things like dikes to control the sea level rise. So what can we do? Well, the main thing that's really important is decarbonizing the energy supply. And in order to do that, we need a real conversation about where we get our energy from and what the options are. There may not be a silver bullet. There probably is a lot of silver buckshot. I've just shown you a bunch of examples of the types of things that might contribute to that. Reducing deforestation wouldn't solve the problem. It could help. 50 times more wind or 700 times more solar, now that would really be a big help. And I think solar and wind technologies are moving along all the time. 60 mile per gallon cars, if we all drove those, that would help a lot. Buildings could be tighter. Sometimes when I give this talk to environmental groups, they boo me when I say doubling nuclear capacity would be significant, and I'm not against that. I'm not against using coal if you can capture the carbon and put it back in the ground. We've successfully done that in tests, and I don't see any reason not to continue to pursue that technology till it gets to the point where it's cheaper and available. So the kinds of things that we're seeing around the world are beginning to give us pause, not because I'm not saying these are due to anthropogenic climate change, but certainly if we keep going the way we are going, we're going to find out if they are, and I'm not sure we want to go there, at least not full throttle. Thank you for your attention.
So as I noted, Dr. Solomon will take questions from the alternating microphones, and we'd like to reserve the first two questions to students, and we'll let her take it away with her responses.
Okay, the lights are pretty bright, but I'll take the person on the left, please.
My question is, if there's increased temperature or it's a warmer climate, we'll have more evaporation from the oceans, more water vapor. Will that increase precipitation and snowfall for us skiers here? And also, will that increase, if it does have an increased snowfall, will the increased amount of white surface area cause a reflection of heat?
Yeah, those are great questions. If we have a wetter atmosphere, you're absolutely right. Rainfall, globally averaged, will have to increase. And there's some indications that it maybe already has. But that doesn't mean that you'll get increased rainfall or snowfall everywhere. Actually, what probably is going to happen is that the dry areas will get drier and the wet areas will get wetter. It's really unfortunate. It'd be great if it was the other way around, but that's not how it is. We're going to rob from the poor and give to the rich. Why is that? Well, partly because those areas that are already very dry, even with the extra moisture, don't get wet enough to rain very much, but they actually export their moisture to the wetter areas. So if you think about a big thunderstorm, for example, it sucks in a lot of moisture from an area way bigger than it is. So the very act of rain produces enough lifting that it just literally sucks in the air from around it. And that's happening on the larger scale in places like the high latitudes. It rains more than the low latitudes because it gets moisture from the low latitudes. So here in the desert southwest type of area, in the dry Intermountain West, I think unfortunately we're in the dry get drier zone. Even if that weren't the case, though, I wouldn't bank on getting more snow, because it's going to certainly get warm enough that a lot more is going to fall as rain. And therefore, it will not be too good for the ski industry. So I really admire the people who've been very innovative in the way they've adapted to this, who are people who do snow plowing. You'll notice that they're now beginning to do both mowing and snow plowing. That's what I call the excellent climate change bet hedge, I'm going to take one from over here, and then I'll go to the other side again.
Hello. I just wanted to ask you, one of my questions that I had, you showed us a lot of graphs and stuff like that. I'm an environmental studies major here at the college, and I know one of the only things that we can have for people such as us that are doing all the carbon stuff, do we have access to your data that we could show other people and maybe,
I'll be glad to talk to you about that later. Did you have a scientific question?
No, I was
Okay.
just asking. That's what it was.
Yeah, let's have questions about the talk and the science. Yeah, next question.
Yeah, you mentioned towards the end of your talk about business solutions that can be achieved through public pressure, and I want to hear your thoughts on if we can create business solutions that make green options more viable for the subsidies that are paid out for petroleum switch to wind and solar, and if that, in your opinion, would work to move us towards a more green economy and less CO2 emissions.
Well, I think that's a conversation that we all need to have, but honestly, I'm more interested right now in R&D being devoted to this problem. So enhancing the amount that we're spending on research and development so that actually we can get better, cheaper energy before we start trying to force it out into the public sector. My own view is that we need some advances in what's available. I'm just very concerned that it's going to be very hard, without making it very expensive, to push it out any other way. Now, one thing that people have done in many states and local communities are things like incentives, tax incentives for green energy. So, if you buy solar and all of that, if you're willing to do that, various communities have decided that they're going to provide tax incentives to foster that kind of development. I personally think that that's, if communities want to do that, that's a great way to go. But I think it has to be at the community level. I'm not here to advocate for, changes in our system nationwide, except that, honestly, I do think we should be putting more effort into research on alternative energies. We put a lot of money into research. We can decide where it goes. Yes?
What made you interested in studying climate change?
I'm an atmospheric chemist by training, and I just find it fascinating that all these chemicals are out there in our atmosphere, doing stuff. So, I don't know. Call me crazy. I just think chemistry is really cool. Yeah. Next question.
There are a lot of skeptics out there that don't believe that humans are causing climate change, as you alluded to in your talk, and I'm just curious, to your knowledge, have you successfully converted any of the skeptics? I mean, does this work?
You'd have to ask them, I hope so, and, I try to tell the story as simply and as cleanly and as carefully as I can. I don't exaggerate. I'm not an alarmist. I think all of those things are hopefully helpful. I've tried to explain to you ways in which I think a lot of things that the skeptics tell you actually are true, but not really relevant to this problem? I mean, yeah, there's all kinds of stuff like that out there. So I hope that's helpful, but I can't really be the judge of that. I will tell you, one thing that really made me happy is that I got a letter one time from someone who was just about to submit an angry letter to the Wall Street Journal. And they said, well, what do you think about this? And they had written all this stuff about how the science was all wrong and that we were making decisions on bad science and that anyway it was going to be costing too much and that anyway maybe the impacts wouldn't be so bad. And I talked him into saying, yes, it's going to cost a lot and yes, maybe the impacts won't be so bad, and out of the idea that the science was bad. And that's really all I'm asking. I think we should draw the line between the two things. Just admit that there is an issue here. I mean, maybe we don't know how to solve it. You can disagree with me that I think when we don't know how to solve something, we should put more money into research. That's a discussion we could have. But let's not argue that CO2 is not a greenhouse gas. That Venus itself tells us that that's not true. Yes.
My question is on a matter that you might have skipped over, was the reversibility of the situation, and I wonder if you could briefly touch on that.
Yeah, it's actually a whole lecture in itself. I was going to do a little snippet of it and realized that was a little too ambitious for a talk packed with lots of other things. Fundamentally, one of the big reasons that what we've already done to the planet will be very, very hard to reverse is that the sinks for carbon, the way the planet can actually absorb the extra carbon that we've put out there, saturate over time. So, the ocean can only take up so much in the surface ocean. And after that, it has to go to the deep ocean. And that takes a lot longer just because the overturning, the ocean is this huge thing that takes a long time for the deep ocean to get up to the top. So you can remove carbon a little bit faster in the beginning when it's going to the surface ocean, but then it slows down. So that's one of the reasons. Another reason, just again, the same thing is true for heat. So the heat that we've already put into the ocean takes a long time to come back out. You can kind of think of it as being, if you had a heat lamp and you had just air under the heat lamp and you turned it off, the air would cool down fairly quickly. But if you had a heat lamp, air, and water, a big pan of water underneath it, and you heated up the pan of water first, then turned off the heat lamp, the air would stay hot a lot longer. The same thing's going to happen on our planet. We've already heated up the ocean. So that's an oversimplification of what happens, but it's largely true. And I don't remember which side I was on, so I think I'll go to that one.
You've spoken mostly about carbon dioxide, and I understand that methane and some nitrogen oxides can be a larger contributor and certainly could be reversed more quickly. And I've heard it said that if we changed our eating habits and all became vegetarians, we might have a quicker effect on global warming than by changing our driving habits or our energy sources.
Yes, okay. Lots of questions in there. Carbon dioxide is indeed by far the largest single greenhouse gas. It's causing about 3 times the effect of methane. Now, the thing that people find confusing is, and this is one reason I just usually don't spend a lot of time on the other gases, is that methane, molecule per molecule, is a more potent greenhouse gas than carbon dioxide. So you'll often hear people say that. Methane is more powerful as a greenhouse gas. Per molecule, that's true. But there's a lot less methane in our atmosphere than there is carbon dioxide. And so carbon dioxide, the total of it, is 3 times as much contributor to global warming as methane is. N2O is actually even less than methane. So if you take them both together and you also add in tropospheric ozone, you can get up to something on the order of half of the effect of CO2. But it's not as big. The main banana is CO2. So that's the reason for that emphasis. It doesn't have anything to do with the fact that Idaho is the 3rd largest dairy state in the country. No, I'm just kidding. But you did ask about vegetarianism. That sort of discussion has been an ongoing one with a lot of debate about how you do the accounting. And you have to be very careful to make sure that when you count transportation of cows against meat, that you also count transportation of vegetables against vegetables. And most of the studies that I've seen that tried to account for everything all the way down the line reached the conclusion, and I'm not an expert in this kind of what they call life cycle analysis of every single place that carbon is expended, but most of the studies that I've seen quoted that seem credible suggest that the most important thing is to eat locally. So if you're eating meat that's been, grown close to where you live, it hasn't been trucked across the country, it's probably better, it's certainly better, I can tell you this, than eating those delicious nectarines from Chile that we can now get in America in the winter. They've got a carbon footprint, the size of Godzilla. So, next question.
I'd like to know your thoughts on the snowball Earth theory, in which rising temperatures change sea level Earth, sea change.
I am not a paleoclimatologist. That is a very interesting issue. As I understand it, people are still debating why what the extent of snowball Earth was and what caused it and why I can't do that one, sorry. It was a long time ago. My only answer to it is, look, the planet was in a very different state also, which makes it very hard. This is one of the real challenges in paleoclimatology. When you start going back past the time when the continents were in the same place as they are today, it starts to get really tough because the ocean circulation was entirely different, everything was different. So it's a field unto itself, and I usually try not to go into things that, are so far outside of what really is relevant to the world that we have today. Yes?
So my question deals with triggers if the ice cap is melting on the north, or the rainforest begins to collapse, or methane, the tundra, bursts methane really fast, and you kind of hit one of those triggers. Is it possible to put it back without, can we recover from that at some point? And then my next question is, like, the tar sands in Canada seem to be like a doubling down by the American economy on oil. And if you have much information on how big an effect the tar sands, if it's developed, could have on CO2.
There's a very, very good letter that just appeared in Nature by a Canadian scientist who's quite green, whose name is Andrew Weaver. And despite being green, he's written a piece in Nature which actually explains that the contribution of CO2 from using the tar sands oil is quite small. So even if we go ahead and use it all, I think the number was it would contribute about 0.5 degree to global warming, and if we use all of the currently known repositories of coal, it's more like 14 degrees. So coal, fundamentally, when you actually go in there and look at what's available and what's likely to be used, it's mainly coal that's the issue. So that's that part of the question. What was the first half of the question again? Oh, triggers, yeah. People have talked about the notion of the possibility of some kind of a abrupt climate change, or people sometimes refer to it as a tipping point. Personally, I kind of shy away from those words because I view them as being a little bit alarmist. We can't readily identify anything that I would call a clear tipping point. Much more of what we know about the climate system is that it changes pretty gradually. Now, the issue of methane is a really interesting one. There is a lot of methane locked up in permafrost. There's also a lot under the seafloor. We do see locally methane being released from a lot of those places. But one of the things that's really weird is that despite the fact that the Arctic was much warmer 125,000 years ago in the last warm period, it turns out that one really warmed the Arctic up a lot by about 2 to 3 degrees. So, we could hit that by the end of the 21st century, for example. But despite being that much warmer, we don't actually see much evidence for significant methane release at that time. And we haven't seen much evidence for significant methane release despite the fact that the Arctic has gotten quite warm in the last 50 years. Why is that? You know, the best guess is that methanobacteria have actually eaten the methane as it tries to filter up out of the soil. So I'm not saying it's impossible, but I just don't think that methane is going to be a tipping point. Another thing people have talked about as a tipping point, which may be a little bit more likely, is the fact that if you get warm enough, you could get hot enough to melt Greenland. And of course, once you melt it, it's not going to reform for many, many years. So I mean, essentially for thousands of years, it'll be gone. And that will presumably warm the planet even more because the reflective ice of Greenland will be gone. That could happen, and that's, you know, but it's not probably going to happen quickly. It's going to happen if we get to 3 degrees and stay there for many centuries. So it's possible, but we won't really know if it is a tipping point in that sense, because I don't think Greenland's going to fall apart all of a sudden. There's been a lot of debate about that question too. This side.
My dad is a fisheries scientist with the Forest Service, and they're finding recently that even single-degree changes in climate are having profound effects on fish and their ecosystems, and even more recently on other organisms and things. And I was wondering how pivotal the study of these vulnerable ecosystems are going to be in understanding climate change, and if there's hope for ecosystems like that that are greatly affected by climate change.
Well, that was what I was referring to, and I said climate science would be a great field for all you young people to study, because stuff's just going to be changing all over the place. Fish is certainly one of them. You know, another thing that is really interesting to me is how tuned into climate change everyone who belongs to the Audubon Society is. You know, because they are used to looking at birds, and they have noticed that the birds are different. There are different ones coming. Certain ones seem to be dying out. Certain ones are, you know, breeding earlier. It's just, certainly we are beginning to see changes in the flora and fauna, and I'm not at all surprised that fish are like birds, except that fewer people put on scuba gear and go down and look at them. So, next.
Yes, I've got a question about actually the chemistry side of things. I was going to say, from a standpoint of when you go back to like the detrimentals of, you were talking about, what is it? It was, what was it? Sorry. Confused, sorry. But I was going to see if there's any other compounds that are detrimental to the climate that you could possibly propose that maybe are used every day in like a household situation that maybe people could possibly stop using, that actually has like a really significant factor in how pretty much the climate's changing. I was just wondering.
Okay.
Sorry.
Well, no, I understand where you're going. I mean, carbon dioxide is the main thing. And that's kind of frustrating to us as individuals, because there just isn't that much we can do. You know, we can change our light bulbs, we can choose not to drive SUVs, we can chip away 10% here, 10% there, but as I explained to you, we got to have an 80% reduction to, you know, and that's just not going to happen until we decarbonize our energy supply, let's face it. So, you know, I wish we could stop debating lifestyle changes. But if you really want to do something, and I'm not, you know, I'm not saying you shouldn't, because every little bit helps, and especially because the carbon that we put in the atmosphere today will still be there in 10,000 years, you know, a significant amount of it anyway, 20%. You know, I've actually really tried hard personally to do things to emit less carbon. So, you know, I do like to take the bus, and I do like to buy local fruits and vegetables and stuff like that. So those are among the things that you can do with carbon. You asked about other chemicals, and you know, certainly one of the other issues is soot. So, you know, if you burn wood in a fireplace, make sure that your chimney is really clean, helps a lot. You put less soot in the atmosphere that way. There's also, sorry? I thought you said something. Yeah, there's also the issue of how much do you really want to invest in, say, diesel cars versus other kinds of cars. Diesel cars, you know, diesel is clean burning in a sense as far as carbon goes, but it actually puts a lot of soot out there. So I would, you know, think twice about that before I'd buy a diesel-powered car. Yes.
Well, I've read, and it makes sense that residents of New York City probably have the smallest carbon footprint around. And as I look at the continuing trend toward urbanization throughout the world, and particularly in China. Can we take comfort in the fact that urbanization may help us constrain carbon dioxide? And if not, what public policy recommendations might you have?
Yeah. Well, I try not to recommend anything except that we all talk about it and keep the science out of the politics, et cetera. But let me, let me see if I can speak to sort of the first part of the question. Which now I'm having trouble remembering. I'm having a senior moment.
The small urban footprint.
Oh, urbanization, right. Thank you. Again, it's a question of, yes, it's true that New Yorkers have probably the lowest carbon footprint of anyone in America because very few of them have cars. So that lops off, a third of the carbon footprint pretty much right there. Not totally, but to a significant degree. So public transportation is much more common in urban areas than in remote areas. On the other hand, we're still going to have to move our food around. We're a big country. So, we're still going to have a bigger carbon footprint than say, Europe, just because of where our stuff is made and how far it has to move. I don't think that urbanization in America is, for us at least, going to really solve the problem. Yes, we can build communities that have better public transportation, but let's face it, out here in the West, we're not going to use it, are we? That's what we are in the West. And personally, I don't think we should, hit ourselves over the head too much with that. If you choose to live in an urban area and you find it more, enjoyable to take the bus or whatever, that's fine. But again, I get back to my same problem. None of these things are going to get us down by 80%. The only thing that's going to get us down by 80% without massively changing our lifestyle is non-fossil energy. So why, maybe we should all have, I'm ready for my electric car. I think it would be a lot of fun to drive. The Prius gets me halfway there, but not as far as I'd like to be. Yes, next.
You spoke regarding, in your discussion of the ice cores, you mentioned that there was research that showed that the isotopes in the ice cores were kind of pointing towards fossil fuels. Could you speak more towards that point?
Yeah, it's actually, I didn't mean to say that the isotopes were in the ice cores. The isotopic measurements are actually in the atmospheric data, more to the point, really. And what we can do is we can measure the isotopic composition of the carbon dioxide in the air of the last, say, 50 or 75 years. And what we find, it's just like, you know that you can date the Shroud of Turin with carbon dating. Well, basically what you can do is carbon date the air. It's the same kind of idea. And what you can find is that the carbon dioxide in our air over the last 100 years is getting older. So basically it's getting very, very old because we're putting so much carbon dioxide in that was in fossil fuels. And that was put there, many millions of years ago when the plants, et cetera, made the oil. So that's why our air's isotopic content is changing. And we can measure that really quite accurately and show that it's very consistent with what we expect. Sure, we can maybe take one or two more over here on the left.
Hi, thank you for taking my question. I'd like to piggyback on the question that was asked over there. And I'm wondering, I know that you said that they had looked at the impacts of the tar sands extraction in Canada. And I'm wondering if scientists are currently looking at those same data here for us in the United States with the increase of hydraulic fracturing or fracking. Because I saw a couple of reports just recently where they were talking about the effects of fracking having that carbon footprint being pretty similar to coal, and it looks like we're really ramping that up in the United States. In fact, they're going to be doing that here in Idaho. So I'm curious if the data that you're using to make those projections that the scientific community are using is looking at that and incorporating that, or if people, scientists, if the scientific community even asking those questions?
Well, sure they are, because that's why you've seen that data, because scientists are asking that question. The thing that we really don't know very well is how much methane leakage there is in those fracking operations, and that's what's being studied. And there was a paper that you're referring to that came out a couple of weeks ago that argued that there was evidence for tremendous amounts of leaking of methane from the big gas fields. That's a very interesting piece of work. It's a little bit controversial because it was not done next to one of those fields that is one of the actively mined fields now, and the older techniques are more leaky. So I do think there's work that needs to be done there to determine how much stuff is leaking to the atmosphere from the fracking process. That is an issue. Yeah, I'll take one last question.
Thank you.
Actually, since there's only one more after you, I'll take him too.
I was intrigued by your section of your lecture regarding geoengineering, particularly putting mirrors in the, or satellite mirrors or particulates. Two questions. One, do you think that this is a good idea to be playing on such a global level with our climate? And two, are there any other solutions that you know that people are trying to come up with?
Yeah, let me speak to the last part, which is other solutions. There has been actually some work on the ways in which you might be able to remove carbon dioxide from the atmosphere. And in some ways, you know, that would be safer because, you know, no one can object to processes that remove CO2. I mean, if we could take the CO2 out of the atmosphere, what's wrong with that? And there's work that's actually, you know, I don't think this is the answer, but it's really intriguing. There is a mineral called olivine, and it actually is capable of absorbing carbon dioxide right out of the atmosphere when it passes over it, especially if it's a little bit warm. And so, you know, the question is, could we have olivine beaches all over the world? And, you know, they'd be green beaches. And that seems like it might be kind of pretty. I'm good with green beaches. You know, and that's the sort of thing that people are actually trying to do, is understand the capability of different surfaces to absorb CO2. People have also talked about not real trees, which won't solve the problem. We can't just plant more trees because we don't have enough square footage to plant enough trees to do very much. But we could potentially make something that some people are calling an artificial tree, that as the air passes through it is actually capable of absorbing the carbon. You know, is that an energy efficient proposition? Can you do it in such a way that you take carbon effectively out of the atmosphere without providing a lot of energy to the thing? So you probably have to have it be solar powered or something. But those are the sorts of other solutions. Carbon removal, I think no one can object to. One of the problems with geoengineering that worries me is that if we reflect energy out to space, yes, we will cool the planet, that's certainly true, but we'll also change rainfall patterns because we'll change evaporation. And exactly how all of that plays out is the sort of thing that people worry about. There are also some very serious ethical questions, because once you start geoengineering, you can never stop. You're going to have to make a commitment to keep going for hundreds of years. Last question.
Thank you. A lot of the data you showed was very technical. How can we make it more understandable to the non-scientific community without losing any of the the scientific value?
Did you understand it? It was kind of technical, but did you understand it?
Yes.
Great. I'm so happy. That's how we do it. Thank you very much.
Thank you for coming. We really appreciate your support of the series. We'll be coming back in the fall, in October, with Steven Pinker and his new book, The Better Angels of Our Nature. Thanks again for being here. Thanks, Susan.